So now let's take a look at the constructive and destructive interference for thin films. This entire discussion, make sure that you're paying attention to this idea of path length. We can have interference from, say, some oil that's sitting on top of some water. And with this type of scenario, we're going to have some light coming in right here, and it's going to bounce at the air-oil interface. Then some of the air is going to be refracted down through the oil, bounce off of the oil-water interface, and come back to my eye. Now we have some path length right here that's going to cause a wavelength shift. And kind of what's going to happen for this guy is these two light rays can now interfere with each other, and it turns out that they can constructively interfere or destructively interfere. So what we can kind of have is we can have colors right, or we can have colors right here where I have some nice blue. In that case, there was constructive interference of the blue light and destructive interference of all the other ones. And then we get these nice wavy patterns because the oil surface is kind of rough. So we're having constructive interference at different wavelengths, different colors. We can have the same thing if we have some two glass plates where we have some light coming in like that, and we're going to have light bouncing off of this glass air surface. Light's going to come down through here, bounce off of this air glass surface, and come back to my eye right here. In the case of these, I can also have constructive and destructive interference. One thing that these two waves have different about them is going to be this path length T right here. And just kind of as an aside, I flew over that Gulf oil spill in 2010 in the Gulf of Mexico. You can see them trying to clean it up right here, and you can kind of see the oil right here. The oil is a lot easier to see. You can kind of see that sheen where here we have oil and here we have water. Now, the whole key to solving thin film interference problems is going to be whether there is a phase shift or not. So this is a very, very, very important slide. It turns out that if we're going from a material with a high index of refraction to that one with a lower index of refraction, I'm essentially going from a slow material to a fast material. In this case, the wave that is reflected is not going to undergo a phase change. We can kind of think of it in terms of mechanical waves propagating on a rope, where we were going from a slow, thick material to a fast, thin one. We had a crest incident upon this interface, and the reflected wave also had a crest. So there was going to be no phase shift. So no phase shift. Now, if there is no change in index of refraction of material, then there really is no interface and nothing is going to be reflected. If, however, we go from a fast material to a slow material, then there is going to be a half-cycle phase shift. Taking a look at the mechanical equivalent, if we have a crest from a fast material incident upon this interface, then the reflected wave is going to be a trough. So here I've undergone a half wavelength phase shift. I've turned a crest to a trough. So very important, keep that in mind. Slow to fast, there's going to be no phase shift. Fast to slow, there's going to be a half wavelength phase shift. So the whole key to this is determining whether we have a phase shift or not, and that's going to be depending on the index of refraction of materials. So if I have a ray that's incident upon some material, and it's in index of refraction 1, I'm going to have maybe ray 1 right here. And then we're going to have ray 2, which is going to bend down into material 2 with index of refraction 2. It's on top of index refraction 3. It's going to kind of bounce back right here. If N1 is larger than N2, which is larger than N3, then I'm going to get no phase shift on between ray 1 and ray 2. So really I'm going to have constructive interference. In this case, the distance that we're traveling here is going to be twice the thickness, because we got 1 and then 2. And so my standard rules for constructive and destructive interference are going to apply. Interestingly enough, if N1 is less than N2, which is less than N3, then I'm going to get a phase shift on 1 and a phase shift on 2, making them therefore both shifted by half a wavelength, and so these equations are also going to apply because they're both in phase still. If, however, the index of refractions were set up such that ray 1 and ray 2 were off by half of a wavelength, then we really just kind of flip the rules right here, and we would use this set of equations right here. So these are the equations. It's up to you to figure out whether there's a phase shift or not and apply the correct equation. So example 35.4 is going to be using this. Essentially what we're looking for is we're looking for the distance between the fringes, x, and so we have some light coming in. It's 500 nanometers. We're going to ignore this reflection, and we're going to consider only that reflection right there, and then that reflection right here. So essentially we're going to be, we know that these slides are going to be relatively slower than air. Here we're going to have fast, and here we're going to have slow. So what that means is there's going to be, here we have a slow-fast junction, so there's going to be no phase shift. This one is going to be a fast-slow junction, so there's going to be a half wavelength shift. So we use the description for destructive interference where there is a phase shift. We're going to say 2 times the thickness is going to be equal to m multiplied by lambda. And we can use kind of similar triangles to say t over x is going to be equal to h over l. So we can say that we have 2xh divided by l is going to be equal to m lambda, where I've simply solved for t. And therefore x is going to be equal to ml lambda divided by 2h. So m is just 0, 1, 2, 3, 4, 5. The length of this puppy is 0.1 meters. The wavelength of light is going to be 500 times 10 to the negative 9th meters. Always have to work in SI still. And then the height of this guy, 0.02 times 10 to the minus 3rd meters. So the distance between the separation is going to be m multiplied by 1.25 millimeters, where m is going to be 0, 1, 2, 3, 4, so on and so forth. Again, the key to this problem is right here. Do I have a phase shift or do I not? And I highly recommend you take a look at examples 34.5 and 0.6 just to get some more practice with this. Just kind of a conceptual example is going to be Newton's rings. If we consider a convex lens in contact with a glass plate, then we have some thickness which is constantly changing, and so we're going to look down on it and we're going to see rings, or circular interference rings rather than lines. A real-life application of Newton's rings would be something that a lens maker would have, which is essentially a cavity, a mold, a master of the lens that they're trying to make. And what they do is they plop the lens on inside there. If there are air gaps, then they're going to see rings. If, however, this lens fits in there perfectly, then the materials are the same, and so there's going to be no rings. Kind of a practical application of all this might be a non-reflective coating, which is going to kind of reduce glare off of surfaces. So we have a glass surface and we don't want to have a lot of glare from it. Well, we're going to lay a thin film on top of it, and now we can have some light coming in. It's going to get a reflection off of that surface. It's going to pass down through the glass, or through the film, reflect off that surface. And essentially we choose the thickness such that this ray is going to destructively interfere with that ray. Now, the question with all this is, is there a phase shift between ray 1 and ray 2? Now, kind of the way that they've drawn it right here is going to be the film has index of refraction somewhere in between air and glass. I'll work in the example problems one where it's slightly different. So here we have a right here, this interface, we have a slow to fast, so we're going to have a 180 degrees phase shift. And then at this interface, we also have a slow to fast, so this one right there is also going to be 180 degrees shifted. So there's going to be no relative phase shift. So we say, okay, well, how do we get destructive interference when there's no relative phase shift? Well, 2t is going to be equal to m plus 1/2 multiplied by the wavelength. So this thickness for the thinnest possible one, so we're going to say if m is equal to 0, is simply going to be equal to lambda divided by 4. Two things to keep in mind here is this is only going to apply for when these two guys are in phase with each other. And again, I'll work an example problem where this index of refraction is different, and there'll be there'll be a phase shift between them. Now, if we were to follow example 35.8 or 35.7, one thing that we're going to be very, very careful to note is this is going to be the wavelength in the film. So if we knew the index of refraction of the film, and we said that the light that was incident upon it is going to be 550 nanometers, how thick does this film have to be for, say, the thinnest film? Well, the thickness is going to be equal to the wavelength in the film divided by 4, and the wavelength in the film is going to be the wavelength in air divided by the index of refraction divided by 4. And so this is going to actually be 550 nanometers. Divide that by 1.38 and divide that by 4. And we're going to find out that the coating thickness, for example 35.7, is going to be 100 nanometers. Again, just be very, very, very careful here. One difference between non-reflective coatings and the example I showed earlier with the Newton's rings is this is going to be the wavelength in the material. And the last thing to talk about here is the Michelson interferometer. I actually used one of these at NASA. We had light coming in to an interferometer, and here we have a beam splitter that's going to essentially reflect some light up this way, reflect some light down this way. This compensator plate accounts for the fact that there's a phase shift for that and not for the transmission here. There's going to be a reflection here, and these guys are going to combine back and come down in right here. And essentially what we're doing is we're taking a look at bright and dark bands. This mirror up here is going to be movable, and so we can move it back and forth very tiny amounts, and we can make measurements on the order of the wavelength of light.